that makes the pointer more or less work is not here. I think it must still be sticking in Jacqueline's computer. So, I want to talk about spiral structure, the impact of spiral structure on secular evolution. This will be an incomplete story because, as I explained, it's a difficult phenomenon and people haven't got to the bottom of it even after 30 years, nearly 40 years of pushing. So let's understand, let's understand what the nature of the issue is. So the first thing to say is that we are interested in launching waves over the surface of a disk of orbiting particles, and we'd like to think of it in the same way that you can launch waves over the surface of a pond by throwing a stone into a pond. But the first difficulty you encounter is that when you throw a stone into a pond, you disturb the water molecules that you hit with the stone, and then they push on water molecules and move their neighbors, and their neighbors then move and push on their neighbors, so that the ripple spreads out from the center. Jacqueline, do you have the magic dongle that makes this thing work? Oh, thank you, Jesus. You'll find it. Right. So it's a local, so the physics is kind of, oh, it sits inside there. Oh, right. Very neat, very neat. Good. So there's a local physical interaction. But what are we going to do? We're going to wave a little gravitational field over the disk, which will disturb the orbits of particles in some region. Those particles will then move on to some sort of different orbits and change the mass distribution in the disk, and their gravitational field will disturb some other particles and so on and so forth. So it's a gravitational field that is going to cause a disturbance to spread through the disk, not the physical pushing of particle on particle. It's going to be particles pulling other particles with their gravitational fields. But the gravitational field spreads at the speed of light through the disk, essentially instantaneously, on our time scale, essentially instantaneously. So we have the problem that we're interested in studying the propagation of a wave, which is in which the mechanical pushing is done by something that propagates very fast and therefore is acting non-locally. So that's an aspect that makes the problem very difficult. But there is a regime in which it's possible to discuss this, rather like doing waves on a pond with some kind of local interaction, and that's the approximation in which we are doing, we have short wavelengths. If I have a ripple in the surface density of the disk, which has a wavelength which is short compared to the distance from the center, if I move away from that ripple, that's going to generate a fluctuation in the gravitational potential. And if I move away from that ripple in any direction, I will find that the gravitational field of that ripple, of fluctuation, dies very quickly with distance away, because the gravity is a long-range force, and therefore the contribution, the extra gravitational field coming from the places of high density is going to cancel rather precisely the reduced contribution coming from places from low density. So as you move away, the gravitational field will die of a short wavelength ripple will die very quickly in by the time you're a few wavelengths away from the rippling, you won't see any longer a significant perturbation. So you will have effectively a local gravitational perturbation caused, so everything will become local again. So that's what people do. They focus on short wavelength waves because it's kind of a tractable problem. Okay, so I want now to describe the derivation of the Lin-Shu-Kalnice, the dispersion relation. So what we're going to do is imagine that we are disturbing our disk. Whoops. How do I get this thing to? It's a mystery to me. It's come. So we're going to imagine that we disturb our disk at some frequency omega, and we're going to ask, what is the wavelength, what is the wave number, really? What is the wave number, the 2 pi over the wavelength of the waves that propagate with this frequency omega? And the way we do this is the traditional way that you do it in plasma physics and all sorts of places, is you, first of all, impose, you say, let's study the response of the system to an imposed fluctuating gravitational field from the potential phi, and then we calculate the density response that produces, and we then, at the end of the calculation, insist that this density response has to be exactly the one that is required to generate this gravitational fluctuation. So for the moment, we're treating this gravitational fluctuation as something we impose, and I want to do this in a way that is different from how it's done, for example, in Chapter 6 or something of Galactic Dynamics, Binney and Tremaine, because I want to show you the sort of the sweet unity that angles and actions introduce into this subject. So the equation that we have to solve is the collisionless Boltzmann equation, the equation that says that the rate of change of the distribution function is given by the Poisson bracket of the Hamiltonian and the distribution function. And Poisson brackets are sort of Poincare invariants. They can be evaluated equally in all possible canonical coordinate systems. So we can write the Poisson bracket like this in terms of gradients with respect to angle variable and gradients with respect to actions. We're going to write that the distribution function is some equilibrium distribution function, so therefore by Jean's theorem a function of the actions only, plus some perturbing bit, some fluctuating bit. This is what we're really interested in, of course, the fluctuating bit, which will, of course, depend explicitly on time, and it will also depend on the angle, on all the phase-space variables, right, not just some of them. And the Hamiltonian will be the equilibrium Hamiltonian, for which we found the action variables, and therefore it's H0 is a function of the action variables only, not the angles, and a fluctuating part, which will be completely general. And then we're treating this as first order. This is small compared to this. So when we work out this Poisson bracket, which involves products of Hamiltonian and distribution function, we need to retain only the case where this is the 0th order and this is the first order, or this is the first order and this is the 0th order, and bearing in mind that the 0th order Hamiltonian and the 0th order distribution function depend only on actions, not on angles. This is all we have to first order. So, and moreover, this that we see here, this gradient of the unperturbed Hamiltonian, the 0th order Hamiltonian, with respect to action, is simply the unperturbed frequencies. So that makes this even simpler. And then we do what we did before, which is we express the perturbed quantities, which are totally general, as Fourier series in the angle variables. We put in explicit time dependence e to the minus I omega t, which we can do because this equation here makes no explicit mention of time. So this equation is time translation invariant, which on general grounds of general physical principle assures me that there's a complete set of solutions to these equations which have exponential dependence on time. So this time dependence is no loss of generality to impose it, and this angle periodicity arises because every function on phase space is a periodic function of the angle variables, and then these coefficients out front. So when we do the Fourier decomposition of this quantity, we are bound to get some objects out front, depending on this integer vector here, and we're going to call this delta f of j by definition delta phi of n. Definition. So we stuff this into our equation, and so all we do is we take these expansions and stick them into this equation here, and out pops this very important relationship here. We can rearrange this. So this is a relation essentially due to Kalnice, which expresses the response. This is the change in the distribution function, which is caused by the change in the gravitational potential. And you see how beautiful this is. The coefficient of this change is given by the gradient of the unperturbed distribution function. On the bottom, we have this difference of frequencies, which is already telling you something you need to sit up and take notice of. We'll return to this later. That if omega happens to equal this, in other words, if our star's frequencies are able to resonate with the frequency of oscillation of the perturbation, bingo, we get a huge, great response on the left for a small input on the right. But this is kind of the central equation of this sort of perturbation in stellar dynamics. And notice just how beautifully simple it is. Once you have succeeded in doing the decomposition of the perturbing gravitational potential into its action angle coordinates, which is on the first sight a slightly bad thing to be doing because you started with a function which depended only on the position, only on x. It didn't depend on v. And you've written it as a function of j and theta, so that sounds like a step completely in the wrong direction and making life complicated. But the good news is that you get this very simple result that we've sort of uncoupled the effects at different values of n. So for each vector n, integer vector n, we have a different equation like this. Okay. So what we now have to do is calculate what this action angle decomposition is of the perturbing gravitational potential. And what we're going to do is assume that the perturbing gravitational potential is a spiral wave. That's what this expression says. This says that it's a spiral wave, a tightly wound spiral wave with, well, it will be tight if kr is a big number compared to 2 pi. So this is an m-arm spiral wave at angular frequency omega. So this is the assumed form of the gravitational potential, and I've justified that on the grounds that we're going to have, I said we're going to have a tightly wound spiral density perturbation, and by this locality of the gravitational field that I've already talked about, the gravitational potential will have the same form in the tight winding approximation. We're going to use the Epicycle approximation to connect position to actions and angles, all right? So RG is the guiding center radius, and that's determined by the angular momentum around the z-axis, and that's an action. That's also known as J phi, or LZ, J phi, it's all the same thing. A here, the amplitude of the excursions radially, I called big X before yesterday, and it's connected to it's basically the square root of the radial action. And gamma is just some ratio of this is the circular frequency at the given angular momentum, and this is the radial epicycle frequency at the given angular momentum. So we have here these explicit expressions through use of the epicycle approximation between the ordinary phase space coordinates, r and phi, and the angle variables, theta phi, theta r, and the actions, one of which is buried inside here, and the other of which is buried inside there. So we take this expression and we replace r by this stuff, we replace phi by this stuff, and you use the magic of exponentials. You can write it out, like this, okay, as a product of four exponentials. And now you put these two exponentials that depend on the angle on theta r. We've now got two. See, theta r has occurred in this expression twice, once through phi and once through r. So we put these two together and do a bit of trigonometry, and we get a factor like this, and then you look up in Gradstein and Ruzick, and you find that an exponential of cosines is always telling you that there's a Bessel function in town, and what we get is this. So this thing here can be written, well, it is this. This is just how you combine the two. This is first year mathematical methods, undergraduates. Brings you to that where curly k is the effective, it is just the wave number, the effective total wave number of the wave. So it's the radial part plus the azimuthal part. Okay, this is the azimuthal wave number, and this exponential of a sine can be written as a sum of a Bessel function. This is a cylindrical Bessel function depending on this and this. So and alpha is the pitch angle, essentially, of the waves. Right? So you put all this stuff together and you get this. So now this is our perturbing gravitational potential written as an exponential in terms of the angle variables, theta r and theta phi. So this is a specific example of e to the I m theta, e to the I m theta minus omega t, right? So this is exactly the Fourier expansion in terms of the magic angle variables, and this stuff in front here is therefore what was called delta phi n before. So that's what this expresses here, right? N is what was a vector, integer n, written as vector n, is now being written out explicitly in terms of its n radius, its n phi, and its n z, right? So, and that's this coefficient here. So we've done this stuff here, does you the angle decomposition, the decomposition of the spiral potential into its action and angle form, which is what we need, right? Because that's what goes on the right-hand side of our master equation. Here's our master equation. We found out what that is for this spiral wave.
Can I ask for a quick,
yes.
A few slides back?
Back?
Just a quick clarification.
Do you mean back? Or?
I do. Oh, sorry, this one, actually.
No, you mean this one?
This one. You're in the definition of A and gamma. Are those kappas the same as your Ks in the next equation?
No. This kappa is the epicycle frequency. So it could be called omega r. I don't call it omega r because it's only valid for infinitesimal, for small oscillations. I'm sorry that there are too many Ks in the problem. Okay, so we've got the angle decomposition, and plugging that. So here it is. This angle decomposition has now been plugged into here. Now what we have to do. This is the hard part. Now what we have to do. So this tells us how the distribution function responds to our imposed spiral wave. Now the tiresome part is we have to find out what the surface density fluctuation is that generates. In other words, we've got to integrate the perturbed distribution function, which is the sum of these delta phi n's times e to the I n dot theta. We've got to integrate that stuff over velocities in order to find the density. And the way we do this is we say, look, I really want to work in these angle action coordinates, theta j, but nature is asking me a question about the boring old xv coordinates. So the way I connect these two together is I say I happen to know from the general principles of classical mechanics that the phase-space volume element, that's this in 2 dimensions, can be written using this simple formula in any system of canonical coordinates. In principle, there's a Jacobian between these two, but the Jacobian is exactly 1 for all systems of canonical coordinates. So what I do is I say, well, I'm supposed to work out this. I don't know how to do d2v in terms of d thetas and djs, so I'm going to multiply by a delta function, delta of phi minus phi prime, delta of r minus r prime, and then put in an additional and gratuitous integral over r and phi in order that I can say that this is d2v, this is d2x, right? These two things are cancelled in some sense by using those two delta functions, and here's f1, the thing I was originally told to integrate. This 1 over r out front is anyway, it's there, of course, because of this, but yes, because if you integrate this stuff up, you get an r. You integrate over the r primed with the delta thing, you get an r, and that r cancels that r, etc. And I want to have an r primed here because I know that d2x in cylindrical coordinates is the r primed, d phi primed. Yes. Okay. So that is so now the d2v can go, and that product is d2v, d2x. That gets traded in by what I really want to do, which is d2j, d2 theta. These delta functions stick around. Okay, now what do? Is I replace... Now this phi primed is a function... it's the same as this, and it's a function of j and theta, and I replace it using the epicycle approximation. Well, we haven't quite got there yet. Sorry. This f1 gets replaced by its what we just solved for up here. All right. And these now get replaced using the epicycle approximation, so that this delta becomes delta of phi minus phi prime. This is phi primed expressed in terms of angles and actions. This is r primed replaced in terms of angles and actions, and I'm going to do these integrals. And I've got 2 delta functions, which means I get to do 2 integrals more or less for free. That's the 2 integrals, of course, that I put in the first place, gratuitously. So, well, sort of. Anyway, I get to do two integrals for free, and the two integrals I choose to do are the integrals over theta primed, j over theta phi, and j phi, which is also called LZ, the angular momentum around the axis. But we haven't quite got there yet. So we do those, and when we do those, in principle, every occurrence of so this thing you see depends. This is the guiding center radius, and this depends on j phi. It depends on LZ, whatever you want to call it. It depends on the angular momentum. So in principle, every time when we do these integrals, every rg should be replaced by an r minus a cos theta r. And similarly, when we do an integral over theta phi, we should find that every phi gets replaced by this. But we're going to make the approximation that we can replace Rg by R, except in where Rg occurs in an exponential and multiplied by k, which is a big number. So e to the I kr, we'd better get this right and put in the right thing there. So when we do this, in this next line, I have done this integration. This derivative arises because we are integrating a delta function involving Rg, and we're integrating it with respect to j phi. And I don't know if you remember what happens when you integrate a delta function with respect to when you integrate a delta function of a function of your variable of integration, you find that these things pop in. The gradient of the function. This is really 1 over drg by dj phi. Really that's how this occurs. So when I do these two integrals, I end up with this expression here, where I've now got two integrals left to do, 1 over jr and 1 over theta r, because I've done the integrals over everything to do with phi, and this is what I have. Now we need to make a decision about what to take for the unperturbed distribution function, and the standard thing to do is to take the unperturbed distribution function to be an exponential in the radial action. There are two ways you can justify this. The simple-minded way to justify this is to say that in the epicycle approximation, this generates for you the Schwarzschild distribution of velocities, which Karl Schwarzschild in 1907 or something gave a reasonable representation to the velocities in the stellar neighborhood. These days, I would prefer to justify this by saying that actually already way out of the epicycle approximation, this distribution function gives you a beautiful representation of the very complicated velocity structure in the stellar neighborhood. I wrote a paper I have published a paper in early 2010 built around models like this, and we published some papers since in our group based on this. So this is an excellent distribution function to represent what happens in the solar neighborhood. So that's what goes in here. That goes in here. Then the gradient of this with respect to JR is, of course, so this is an exponential in JR, so the gradient is simply going to be the function itself times kappa over sigma naught squared, probably with a minus sign, minus kappa over. So that's what this is, etc., etc., etc. We've got some Bessel functions. You can look up about the integrals of those. So when I've done the theta integral, this is what I get. And Gradstein and Rizek enables you to do this integral here of a Bessel function times an exponential, and you come down here. So this is an expression for so all the integrals are done analytically. This is an expression for the surface density generated by that tightly wound spiral perturbation. And you can simplify this a bit using this. Sorry, this is a Bessel function of the other sort, not the J sort, but the exponential, not the oscillating sort, but the exponential sort. And kappa is a reasonably it's sort of a wave number, right? This is the wave number, and this is some kind of normalizing whatever. S is a measurement of the difference between the frequency that you're exciting the system at and the frequency that's perceived at co-rotation. So this is going to vanish at co-rotation and be negative inside co-rotation, positive outside co-rotation. This is just some conventional definition. So it's a way of packaging this sum of Bessel functions up. And then with these definitions, this result that we have can be written down like this. This is just traditional. And now the final step is we have to impose Poisson's equation. In other words, we have to say that this surface density is what's required to generate the gravitational potential we first imposed. For a tightly wound spiral wave, this is this locality assumption. We have a nice simple relationship between the surface density and the imposed potential. We said what this imposed potential was, and here it appears. So we insist that this relationship is the same as this relationship, and that gives you this Lin-Chu. This gives you this final dispersion relation. So this S is a function, I'm afraid we've lost it, it was on the previous page. S is a function of omega. The frequency, I said we were going to derive the wave number as the function of the frequency. So S is where the frequency has got buried, unfortunately. This notation is due to Toomey, and don't blame me. Well, no, it's not. Sorry, it's not. Sorry, it's due to Kalnice. But anyway, this is the conventional way that it's done. And so this is carrying the frequency of the excitation, and this is where the wave number is coming out. Okay. Okay. So this is, here's reminding you what S was. Sorry. Okay, so S rises from -1 at the inner limb-bound resonance, because at the inner limb-bound resonance we have that I must have got the sign wrong here, actually. This must be omega p minus omega, because at the inner limb-bound resonance, omega is bigger than omega p, and S should come out, and m times this is equal to kappa, so S is supposed to come out as -1, so I must have got the sign wrong there. So this is correct. At inner limb-bound resonance, S is -1. At co-rotation, it's nothing, of course, because omega minus omega p, the circular speed frequency is equal to the patterns thing, and at outer limb-bound resonance, S becomes 1. So S is a sort of, the way to think about S is, in some sense, I told you it was where the frequency of the excitation of the disk is buried, but it's become a function of position because of the way that we have used kappa as a normalizing, as a way to make this into a dimensionless variable. So it's become something which varies with radius. Okay, so what does this tell us? It tells us that at the limb-bound resonances, the right side of this equation vanishes, right, because S squared is going to be 1 at either limb-bound resonance, and therefore this side has to vanish. That means that most of the time K vanishes, so we're going to be losing our tightly woundness. Well, F times K has to vanish. The other thing that's going to happen is that when at co-rotation S is going to be 0 and this right side is going to be 1, and it turns out that if the disk is stable to axisymmetric disturbances, if it has enough heat to be stable against just pure Jeans instability, this left side here cannot achieve the value 1, which means you can't find a value of K. The waves simply cannot get to a region around co-rotation. So the waves are going to be excluded. There's going to be a forbidden zone around co-rotation. And the other thing to say is that this F, which unfortunately was defined in terms of the sum of Bessel functions and stuff, so you'll have to believe that this F behaves a bit quadratically. It behaves like K times 1 minus BK, where B's a number bigger than 1, sort of qualitatively. So there are two values of K at which it achieves a particular, F achieves a particular value. So when there's a solution, there are two solutions. There are two values of K for given omega. So what's the bottom line on all this? So we have a diagram that looks a bit like this. We have we have a normalized, we have K increasing along here and omega happening up here. Now this diagram is probably plotted the wrong way up in the sense that this thing contains the frequency, and I said we were going to get k as a function of omega, and indeed we are going to get k as a function of omega. So this is really the independent variable. And the question we have to ask ourselves is, given a certain frequency, what k values can I have? So I choose something along here and then drop down and find out what the wave numbers are at which the disk is capable of sustaining an oscillation at that frequency. And you can see that as we get towards co-rotation, where s is naught, so s is a measure of the frequency, but it's naught at co-rotation, it is 1 and minus 1. It's minus 1 at inner Lindblad resonance and 1 at outer Lindblad resonance. So here are the Lindblad resonances. Here's co-rotation. And the curves of k versus omega are these, which are labeled by Toomre's Q parameter, which, is it defined on the previous slide? No. Is it defined on the next slide? Yes. It's a measure of the hotness of the disk. So here's Toomre's Q parameter. It's got the velocity dispersion, and then it's got the surface density, the gravitational constant, and the epicycle frequency, making a dimensionless number. So the bigger Q is, the bigger the velocity dispersion is relative to the surface density. So the hotter the disk is. So with a hot disk, that means a large value of Q, there's a big forbidden zone. There's a big zone here. From here, so if Q is 2.5, from S is 0.8 down to nothing, there is, in this region, which is around co-rotation, the disk is incapable of sustaining waves. Is incapable of sustaining waves at that in that zone there. And as you lower Q, so you go to colder and colder disks, the region capable of sustaining spiral structure grows and grows and grows until you get to Q equals 1, when it extends all the way down to the co-rotation and the disk becomes even unstable to axisymmetric disturbances. So it's not probably very interesting to discuss anymore. Okay, then there are two. So if we're capable of sustaining waves, there will be a small value of k and a large value of k. So the large value of k will be tightly wound waves. The small value of k will be less tightly wound waves. And therefore, remember, we went into this enterprise saying that the waves were tightly wound. We used an expression for the gravitational potential generated by the waviness that assumed tight woundness. So we do have to worry about using values of k which are very small, because we'll be violating our assumptions. But the main idea is we have these two values of k. So what does this tell us about the dynamics of a disk? Well, to fill the picture in, we need to do one more thing, which is to take this relationship of k as a function of omega and work out d omega by dk, the group velocity of the waves. So Toomre did that. Doesn't say here when, but anyway, he did that a few years after this dispersion relationship was derived, and the picture that emerges from that is the following. Suppose you launch from the. The point is these waves do have a non-zero group velocity. So wave packets are going to propagate through the disk. So when the disk is capable of supporting these waves do propagate. And the way they propagate enables you, or the propagation is such that you can make the following picture. If you launch from the inner Lindblad resonance a short trailing packet, so you start at the inner Lindblad resonance a short trailing packet, you'll find you can propagate that has a group velocity which causes the packet to propagate outwards from the inner Lindblad resonance until it gets to co-rotation. Well, until it gets to the edge of the forbidden zone around co-rotation, where the two branches come together, right? So if I'm away from the edge, this point here is the edge of the forbidden zone. At the edge of the forbidden zone, two branches become identical. So I start with a short short leading wave. Did I say? sorry, this is wrong. I want a short leading packet. So I take a short leading packet. That means that K is negative. It moves out from the Lindblad resonance until it gets to here, where it becomes a long leading wave and heads off towards the Lindblad resonance. At the Lindblad resonance, this long leading wave morphs into a long trailing wave and reverses its sense of propagation. So it propagates from there as a trailing wave. As a trailing wave, it propagates out from there back to this zone around co-rotation, where it becomes a short trailing wave, and then it heads off, and then it goes off back towards co-rotation, getting a shorter and shorter, where K grows. So you can see as you go along here, as you go along here, K is getting bigger and bigger and bigger, and eventually the wavelength is getting shorter and shorter and shorter, and the wave is simply going to it's going to dump its energy in heat. So I think I've got that. Oops, I've confused everybody somewhat with that. So let's do it. Let's see if we can do it again. We start somewhere here outside the inner Lindblad resonance, and I launch a short leading wave, and that will propagate out here, changing its wave number, keeping its frequency the same, its omega the same, but S, remember, involves kappa and therefore is changing. Here it bounces off the forbidden zone around co-rotation and turns itself into a long leading wave, heads back out to the Lindblad resonance, where it changes its direction again, comes back out of here, and goes into here it goes from being leading to trailing, and it comes out here as a trailing wave, which gets tighter and tighter and tighter and tighter and turns itself into heat here. So that's the life cycle of one of these waves which you launch in the disk, as far as this kind of theory goes. And so what you notice is that we started with a short, tightly wound leading wave, and this tightly wound leading wave became a loosely wound leading wave, which became a loosely wound trailing wave, which became a tightly wound trailing wave. So what we're seeing here is the winding up of our waves, almost as if, in a similar way, to if they were material objects. Because if you, in a differentially rotating disk, draw on a leading wave, it will unwrap through differential rotation. At some point it'll become more or less radial, and then it will become trailing and become tighter and tighter wound trailing, and that's exactly what these waves are doing. But crucially, the wave energy is eventually dumped at the Lindblad resonance, at the inner Lindblad resonance, as heat through the wavelength becoming extremely short, which is, it's also how the sound waves in this room will dissipate and turn into heat. It's how waves generally turn into heat, by their wavelength becoming short, and so distributed processes can operate. So that's what physics you get out of the linear theory. That's linear theory of spiral structure, and it's rather limited. What we need now to complete the picture is what happens as those leading waves turn into trailing waves at the Lindblad resonance. So at this point, they unwind and so instead of being tightly wound, they become not tightly wound, and our approximations that we've been working with rather fail. But the way I like to think about it is that the up, down, up, down, up, down has become a sort of blobby thing which gravity can get a hold of and give it an impulse inwards. And if the random velocities in the disk are small enough, gravity gives it a big impulse inwards, amplifying it before or even during the time in which differential rotation shears it out and turns it into an increasingly tightly wound trailing wave. So you find that there is an amplification that takes place, at that point, which is a sensitive function except I've lost mine. There we go. Which is a sensitive function of this 2-Marie Q parameter. When as Q approaches 1, the amplification of the wave packet that happens as it morphs from leading to trailing diverges. It's also a function of this factor x, which is a measure of how tightly wound it is. There's a characteristic wave number that occurred in this problem. I'm afraid I didn't point it out, but it does. So the characteristic wave number times the radius divided by the number of arms in the spiral is a measure of tight windedness, of tightly woundness. So when that's small, that also enhances the amplification. So if Q is small and this is small, you can get some very large amplifications at this moment of turning from leading into trailing. Okay, so what's the bottom line on all this? It's that cool disks are very responsive systems because it's easy to launch a wave which goes through this amplification process and emerges as a much larger wave. Another thing that we learn from this is that spiral structure inevitably heats the disk. The original conception of Lin and Xu had been that we could understand spiral structure as in the same way that you would pretty much understand a laser to work. You've got some kind of medium which provides some little bit of amplification, but mainly you've got a resonant cavity. That you would have waves that will be trapped between resonances, just as in a laser the light is trapped between the end mirrors of the laser, and then you would be able to just tweak the waves a bit with stellar dynamics. A little bit of amplification would go a long way, and you'd find you had a nice resonant system. This is also how you can think about atoms in reasonably large quantum numbers. But it's a sort of electron wave trapped inside some resonant cavity. But this picture is fundamentally flawed because of this tendency for the wave energy to be turned into heat, to be thermalized at the inner Lindblad resonance. So that it's a sort of primary property of spiral structure that it heats the disk. I described this, so earlier this morning I described this from another perspective when I said that a steady spiral pattern has got to move points in the energy angular momentum diagram along lines of slope with the slope of the pattern speed, and that there'll be strong interactions only at the resonances, and at the inner Lindblad resonance, I can only take circular orbits and shove them to being rather eccentric orbits. So this is this heating process we're seeing from another perspective. Okay, so the spiral structure it inevitably heats the disk, and I would say that's what it's there for. It's there in order to enable the galaxy, as I say, to transport angular momentum outwards, which is the secret to increasing the entropy of the disk, i.e. to heat the disk. So that's exactly why it's there. Right. I think that's probably all we need to say on that. This is from Zhang's, Tom Zhang, who was Tumre's student. This is a diagram taken from an article by Tumre in 1981, a conference proceeding in 1981, but it is from Zhang's thesis, who was Tumre's student, which illustrates this point. So here we have a tightly wound leading disturbance launched into a tractable disk. It's a disk with a totally flat rotation curve, etc., and all the response of the system is calculated using this kind of linear response theory that I've been describing mathematically. So as the disk evolves, this thing unwinds. You can see it, I think, unwinding. And here we are at the crucial moment where this leading wave is turning into a trailing wave. And here we are a moment later, or a very short while later, and you can see this very weak leading disturbance has become an extremely strong trailing disturbance, which evolves some more and winds up and winds up and winds up. And eventually, here it is down at the inner limb resonance, heating the disk. It's now fading because it's turning its energy into heat. So here, this thing is given an impulse. These rather compact arms are given an inward impulse by gravity, which causes this growth, and then this growth leads to a winding up and a heating. So this is not based on tightly wound. So this stuff isn't done with tightly wound waves. It's done with the proper equation, which I didn't point out. So it's done with this equation here. Whoops, this stuff here. But you see that the picture that we've extracted from thinking about waves running through the disk and being amplified and then thermalizing themselves is about right. So I think it's good at this point to pause for a moment and ask: so why did it not turn out that the Lin-Shu program was fruitful? It's surprising that it wasn't fruitful because the dynamics of our disk is governed by the coupled Poissons equation and the collisionless Boltzmann equation, and neither of these equations mentions time explicitly. They only involves derivatives of time, but there's no mention of absolute time. And that means, on general grounds, that there's got to be a complete set of solutions to the linearized. If you linearize these equations, you've got to be able to find a complete set of solutions which have a time dependence e to the nu t. Sorry that I didn't get this to take up properly. Okay, where this frequency could be a complex frequency. This is a general principle of physics or group theory or whatever you like. It's inevitable that those linear equations in which there is no mention explicitly of time have a complete set of solutions which behave in this way. And if the system isn't completely stable, then the observations are going to be dominated by whatever is the most slowly growing, whatever is most rapidly growing, the most unstable mode. So the idea was that on these general grounds, we must be able to find a complete set of solutions that behave like this. It's extremely plausible that some of these solutions are unstable, that some of them have frequencies, these complex frequencies nu, which have positive real parts, and so they grow. And the observations are going to be, they grow, and then will also, inside this disk, be genuinely dissipative processes. For example, the gas, the spiral in the stars is going to move the gas around. The gas is going to bang into other gas and literally turn its energy into heat. And that energy has to be drawn from the stellar spiral, and so at some point the stellar spiral will stop growing because it'll have energy drained out of it by the genuinely dissipative processes in the gas, and so the system will settle into a fairly steady state in which the gas is constantly being driven by the stars, and the stars are kind of stable, but the pattern of motion of the stars will be dominated by whatever the most unstable mode is, and so that's what you will see in your pictures, right? So it seems kind of inevitable that this program is going to work, and we've just seen that this program doesn't work because the waves basically they're already damped at the level of stellar dynamics. Already the stellar dynamic evolution leads to the wave energy being dumped in heating of the stellar disk. We don't need any gas in order to cause dissipation. And this is perplexing because the equations we started with are time-reversible equations which shouldn't have dissipation. So what went wrong? I think it's an interesting piece of physics, and the interesting piece of physics was basically pointed out by Van Kampen in the context of electrostatic plasmas. It's that the fundamental equation, so this equation is almost the equation you've seen before, where delta Fn was written as this gradient divided by this frequency difference. So this equation here has been honestly obtained, almost trivially obtained, and completely honestly obtained out of the collisionless Boltzmann equation. It was a mistake to divide this equation by that, because as you learned already at high school, you should never divide by a number which might be 0. And this number could indeed be 0. In fact, this number on resonance is 0. So you're not entitled to make the division like this. And the solution to this equation is not what we wrote down, and not what Zhang and Toomey used, not what everyone tends to assume is the case. It's this. So here is what we had before, plus some function of the actions times the delta function, a Dirac delta function in this thing which might vanish. So if this doesn't vanish, then we're back to our old solution. If this does vanish, then we don't exactly have our old solution. We have our old solution plus this in the back here. If you take this solution, so Van Kampen pointed out in a rather simpler context, if you take this solution, you can satisfy the self-consistency condition. The condition. So remember, the first phase was to get this response of the distribution function to the imposed gravitational potential. The second stage was to calculate from this perturbed distribution function the perturbation in the surface density and insist that that's exactly the surface density perturbation required to generate this. So this self-consistency condition of the second stage can now, with this stuff here, can be satisfied for any value of omega, not for particular values of omega, for any value of omega. It turns out you can satisfy this. And it turns out that you can satisfy it for, that now modes can be found for any real value of omega, and these modes are complete. So the problem, the difficulty that the Lin-Shu program ran up against was that they were assuming that the solutions that the normal modes, the wave solutions that they were finding, were a complete set of solutions of the governing equations, so that any initial condition of the galaxy could be written as a linear combination of these things. That's why we are, in any physical problem, that's why we're interested in the normal modes, because they provide, they enable us to understand what's going to happen from any initial condition. But they were wrong. They were dealing with a subset only of the complete set of, well, actually they were dealing with solutions which weren't normal modes in a proper sense, because they were working from the wrong equation, and certainly their solutions didn't form a complete set. So they don't provide a basis on which you can predict the future. So that's kind of what went wrong. And I think this is a generic problem. I think it's worth dwelling on this, because I don't think this problem arises only in the context of spiral structure. This is a generic issue when dealing with the stability of stellar systems. So, just a final word or two about the driving of spiral structure. I guess I said some of this already in reply to questions after the first talk. What we discover, what the bottom line, the important point is that disks are responsive systems because they have a source of energy within themselves. If they can transport angular momentum outwards, they can shift their matter distribution so as to liberate energy, gravitational energy, which they can turn into heat, so that they can increase their entropy. So anything which enables them to transfer angular momentum outwards will enable them to release from inside themselves gravitational energy, which can increase the entropy of the universe and therefore is a good thing. And we've discussed a little bit a specific mechanism by which this happens, namely the launching of spiral waves, which then get amplified and then thermalize, okay? But but the generic point is perhaps more important, that these are responsive systems, and they have a general route to increasing their entropy, but they need a little help. They just need a little help along, that's all. Okay, so the galactic halo, as said this morning, is a lumpy thing. The SDSS has shown us that it's a lumpy thing, and we have to presume, and lambda CDM predicts that, the dark matter distribution that is really what matters rather than the stellar halo is also a lumpy thing. This is a picture, of course, this is a famous field of streams picture. It hasn't come out very well, right? But this is the Sagittarius stream. So these are star counts from the SDSS. So the number. This is created by counting stars and in a particular color range. And you see that here is the Orphan stream. This is the Sagittarius stream. This is the Monoceros. Over again. See, the point is it's full of lumps and bumps. It's very far from smooth and homogeneous. So these lumps and bumps will be stimulating the disk, applying torques to it, and we have to expect that gives rise to fluctuations. Sorry, that launches waves, which carries angular momentum outwards, which heats the disk. This is a famous picture from the collaboration that's been studying M31. This is M31, our neighboring giant galaxy, and this is again obtained by counting stars in vast regions. And so the bottom line of this is that the outer regions of M31, here's M33 down here, this whole vast field, this good slice of the local group, is full of not only satellites, the numbers, these are marking, the Roman numbers are marking satellites, but it's full also of streams and irregularities of every sort. So what we know is that there's no such thing as an isolated galaxy. Galaxies which have, in the past, we thought of as isolated, we now understand, as a result of studying features at very low surface density, are living in a noisy environment where there are streams and lumps and whatnot moving around. We don't have a sufficiently satisfactory understanding of what this all is, but we know it's a noisy environment, and so it's reasonable to think, but hasn't been established, that the disk picks up on this noise and uses it it's stimulated into increasing its energy. So when a lump of matter, for example, when a lump of dark matter sweeps through pericenter, its tidal field is going to launch a wave into the disk being a responsive system that's capable of amplifying the noise. And the classic example where this is undoubtedly happening is here. So this is M51, and is this NGC 5195, something like that. So it's clear that in this case, the very beautiful spiral structure of M51 is stimulated by this companion passing by. And numerical models have confirmed that this really works. So here there's a massive spiral being launched, but in galaxies without this kind of massive and visible companion, I think we have to imagine it's reasonable to suppose that there are. Well, I think we know there are smaller companions, and many of them dark, which will be doing something similar on a much less dramatic scale. Okay, and another highly relevant point that I guess, so grand design spirals are not prevalent. That was obviously a grand design spiral because many galaxies will be responding to several weak stimuli from miscellaneous satellites, possibly dark satellites. Many spirals, well, more than half of spirals, have some kind of a bar at their center, and the rotating bar will also launch waves into the disk. It will excite waves in the disk. The waves in the disk won't actually have the same pattern speed as the bar, because the bar will be rotating too fast for the convenient propagation of waves in the outer disk. But nonetheless, it will be shaking the disk. The disk will be generating waves in the disk, and those waves will amplify as advertised. So I think that's okay. So here, that's basically all I wanted to say. Here are the sort of summary of conclusions of what I hope to have convinced you of in these talks. There are two key approximations in stellar dynamics. One is that the system is collisionless. The other is that the orbits are quasi-periodic. There are important violations of both of these approximations, which lead to significant astronomy, but those are always our starting points of saying we have a collisionless system and we have quasi-periodic orbits, and let's go out from that starting point into a more sophisticated understanding. What we should be doing is decomposing galaxies into chemically defined subpopulations. So I haven't talked at all. I've deliberately avoided the issue of chemistry, but I just want to say now that stars that are physically distinct from each other because they have different chemical compositions, either in terms of Fe over H or in terms of alpha over Fe or whatever, each such subpopulation has to have a distribution in phase space which is distinct from every other subpopulation. So the task we have to do is think about each chemical subpopulation as being characterized by a distribution of stars in 3D integral space, in action space to be concrete. In principle, we can use any coordinates for integral space. So galaxies should be considered as being populations, a series of populations of stars living in this integral space, and in principle we can use any coordinates, but the actions are the only integrals. They're special integrals because they allow us to define canonically conjugate variables, the angle variables that give us a complete coverage of six-dimensional phase space. These magic coordinates come with a bonus, or two bonuses. One is that the actions themselves are erratic invariants. In other words, as if the potential of the galaxy slowly evolves slowly on an orbital timescale, then the numerical value of the action stays the same even as the orbit evolves, and the angles have the bonus that they have a trivial time evolution, namely they increase linearly in time. Historically, there's been a major problem of exploiting this wonderful simplicity, this power of angle action variables, because there's been a lack of expressions for the angle action variables of generic coordinates. We've been working in recent years to fill this gap. I haven't talked about this, but I think it's important that there is a numerical procedure for constructing the angle action coordinates associated with any gravitational potential, and I think that changes the intellectual map to some extent. It makes these very much more useful than they have been in the past. The structure of phase space can be profoundly changed by resonances, and here it's worth noting that in the past it hasn't been obvious. In fact, in many cases it isn't really obvious what the underlying unperturbed Hamiltonian is. Sometimes we are literally perturbing the gravitational potential with some wave or some satellite or something or other, but sometimes what we see is we write down a perfectly boring gravitational potential and calculate the dynamics, and we find that there are loads of resonances interacting with each other doing funny things, and then it's not immediately apparent what the underlying Hamiltonian is. And this business of numerically constructing angle action variables, I think, fills that gap and enables you to talk in a meaningful way about what the underlying integrable Hamiltonian is and what the perturbing part is. Resonant trapping can easily lead to chaos and mixing, which undoubtedly play a very important role in galaxy dynamics once you start to think about the chemistry of stars. Fluctuations are very important because and generically, the fluctuating component of the gravitational potential will be trying to push the system towards thermal equilibrium. So it will be moving angular momentum outwards, it'll be increasing random velocities, things like that. It will be increasing the central concentration of the system. Perturbation theory enables you to study how resonances and fluctuations happen. Perturbation theory, which I've been formulating systematically in terms of angle action variables. The orbit average Fokker-Planck equation describes how stars diffuse through action space, which is just fundamental to the long-term evolution of galaxies, to the secular evolution of galaxies. And an important result we recovered was that stars can diffuse through phase space only if the power spectrum of the fluctuations has power at one of their resonant frequencies. So from the phenomenology of solar neighborhood heating, we can infer how the diffusion coefficients that associate stars in the solar neighborhood vary with action. We found that they scaled with the square root of the action, and it's an unfinished piece of business to understand why they scale in that way. Star cloud scattering doesn't satisfy, it doesn't give you such rapid growth in the diffusion coefficients as the observations require. So I think it's pretty clear that star cloud scattering isn't the only process that's at work in scattering stars in the solar neighborhood, and it's not entirely clear whether this is a worrying situation or isn't. The other very important player is undoubtedly spiral structure. Periodic spiral structure shifts stars on resonances and only on resonances, heating at the Lindblad resonances, but shifting stars but not heating them at the co-rotation resonance. The dominant thing, in fact, that a spiral structure does is to cause this orbit swapping around co-rotation, to move stars that were inside co-rotation, outside co-rotation, and stars that were outside co-rotation, inside co-rotation, thus scrambling the chemistry of the disk. But if you don't take account of, if you're not thinking in chemical terms, you don't even notice this is happening. Angle action variables provide a compact expression for the eigenvalue equation describing normal modes, but this equation is hard to solve. I haven't talked, in fact, about solving that equation. The delta F is equal to something to do with delta phi n divided by n dot omega minus omega pattern. But it is possible to solve that equation, but it's not clear that it's worthwhile to do it because the solutions you get by solving that equation are not a complete set of solutions, so they're not capable of representing arbitrary initial conditions. Instead, we focused on the propagation of tightly wound spiral waves, and we found basically that they wind up just as if they were, not exactly as if, quantitatively not as if, but qualitatively as if they were material arms. They rattle between inner Lindblad resonance and co-rotation, winding up and being amplified as they morph from needing to trailing. So disks are responsive systems, which heat at the inner Lindblad resonance predominantly, where the wave energy is thermalized. Galactic halos are noisy. I didn't talk about, one thing I haven't talked about, which I probably should have done, is the launching of vertical waves. So if I shake the disk in and out of the plane, I also can launch waves through the disk, and these again will thermalize, thickening the disk. So disks are responsive systems. Warps in spiral structure, I think it's quite likely, are responses to the noise in the environment of the galaxy, which we know is considerable. Bars will also launch waves through the disk, but not synchronously, so at a different pattern speed at the pattern of oscillation of the bar. And with that, I'm all done. Thank you. Questions? There's a question here.
Hello. I would like to ask, is it possible the spiral waves to cause or to have contribution to the flat view of the rotation curves in the spiral galaxies?
To the rotation curve?
Yes.
Well, they do create these ripples, right? So I think I mentioned that the terminal velocity curve has ripples of on the order of 7 kilometers a second. And when you show that to a particle physicist who's interested in dark matter halo, he says, what is this? And it's just that obviously the spiral wave is applying torques to the stars as they, pulling them into the wave and then slowing them down as they come out. And that causes a superficial fluctuation in the rotation curve. In the long run, the spiral wave, I suppose, we have to expect modifies the shape of the rotation curve in the sense that it is moving, it's increasing the central, it's one of the many things that increases the central concentration of the galaxy, right? So it moves angular momentum outwards, which enables stars at the inner limb bladder resonance to move systematically inwards, thus increasing the central concentration, and so changing on a long time scale, changing the mass distribution in the galaxy and the circular speed curve. Does that answer you?
So it's not possible to have contribution or to make this flat view of the...
Well, what do we mean by the rotation curve? What do we mean? By the rotation curve, I mean the circular speed curve. I mean I take this galaxy and I azimuthally smear the mass so as to get rid of all non-axis symmetries. And the rotation curve, I mean, is the circular velocity, is the plot of circular velocity versus radius when I've done all that. So I've deliberately erased the spiral structure before I speak about the rotation curve.
Thank you.
Yes, question?
Yeah, about the fact that angular momentum being transported out leads to a higher entropy system you mentioned. I think you connected it to noise, to heat. Is this necessary, or just the transfer of angular momentum preserving perfectly circular orbits would also lead to a higher entropy state?
Well, if you
being a natural process.
Okay. But I think it's just a brutal fact that if you do transport angular momentum outwards, because the Hamiltonian by the action is equal to omega, and omega is outward decreasing. I mean, the circular frequency goes down as you move outwards. So if you move angular momentum from the stars in the middle and give it to stars on the outside, the stars on the outside have to absorb, they have to increase their energy in order to carry this extra angular momentum. And the stars on the inside can reduce their energy but the energy released on the inside is more than the energy required on the outside. The energy tied up in circular motion is by doing this, you're going to lead to inevitably to a situation where less energy is required to be tied up in circular motion. And the spare energy, because energy is conserved, has simply got to go into other motion than circular motion. Did you get that? And, of course, that's what you expect to happen. I mean, it's the fundamental... The galaxy, this galaxy starts out in a very peculiar distribution in phase space of loads of, as indeed the solar system did, with loads of particles in a very special, on nearly circular orbits, nearly in the equatorial plane. And this is any random process, any disorganization will move the system away from this special configuration into the broader opportunities offered by phase space, and that will be irreversible. What galaxies are busy doing, just as the solar system is busy moving everybody to slightly more eccentric, slightly more inclined orbits, and one day it'll get out of hand and we'll be doomed.
No more questions? Okay, yes, remember that Professor Binney is leaving after lunch, so that will be your last chance to talk to him. Okay? Thank you very much.